Moving into Unit 6, which is Systems of Equations, we're going to start off Lesson 1 by looking at how to solve a linear system. A definition of a system of equations is a set of two or more equations in a coordinate grid. If you have two equations, you will have two unknowns or variables. And we're going to look at the graphs of the equations, which are lines if they're linear, right? And then graphically, AB is a point on lines 1 and 2. Then AB is a point where lines 1 and 2 will intersect. And that's what we're looking for as our solution to our system. Lines can intersect at a single point. We call these equations or systems consistent. If they don't cross at all, they are inconsistent. It also means that they are parallel. And if they are infinitely many points, they are called dependent, though they are also considered consistent because they have an answer. Okay. So ways to solve is by graphing or substitution or elimination. Graphing is not the most reliable because they don't always cross at a whole point. But let's see what these look like on a graph. So this one, if we solved it, would be y equals -3 over 2x plus 9 over 2, or that's going to be like 4.5 when you graph it. All right, so subtract the 3x, divide by 2. That's where I got that. So 1, 2, 3, 4.5 is this y-intercept. Down 1, 2, 3 over 1, 2. Down 1, 2, 3 over 1, 2. And so here's this first line here. And then your second line, again, subtract 2x, divide by 5. So -2/5 x minus 1, 5 over 5. So y-intercept is here, going down 2 over 5. Looks like we're going to hit right there. You could also go up to left 5 to get another point there and make this line a little straighter. Okay, it looks like this is our point of intersection, which is at 1, 2, 3, 4, 5, -3. But I would need to plug that into both of those to be sure of that. So a more reliable way to do this is to solve by substitution or elimination. So for substitution, you are isolating a variable, so solving for like y or x like we did up here, and then substitute that into the other equation so that you can then have just a single variable equation that you're solving for. And then you can solve from there. So like I always look for things that are easy to solve for when I'm doing this. This y is pretty much already by itself. There's no lead coefficient. Up here, everything is divisible by 3, so it would be just as easy to solve for that y in this particular case. For this example, I'm just going to subtract 7. And so I get y equals 10x minus 7, or 10x minus 7 equals y. This value for y is what's going to replace this y in the first equation, so the one you did not manipulate. Always make sure you plug into the opposite equation. Otherwise, you will get all real numbers every time. So 6x minus 3 times y, and again, I'm going to substitute in my y value, equals 3. Notice everything else will stay the same. So I'm just plugging in that 10x minus 7 where there was previously a y. From there, I'm just going to solve it. So 6x minus 30x plus 21 equals 3. Subtract 21, combine like terms here. So negative 24x equals negative 18, divide by negative 24, and x equals, both those reduced by negative 6, so 3 over 4, all right? Again, that would have been hard to see on a graph, which is why substitution works best here. So now I need to figure out what my y value is if I know my x value. Well, if I come back over here, I've already solved for y. I know that it's 10 times x minus 7, and so I'm just going to plug that 3/4 in right there. Don't forget parentheses. This is multiplication, not addition. And so this will cross reduce by 2, and that's 5, and that's 2. So 15 over 2 minus, I'm going to go ahead and get a common denominator here, 14 over 2. So y is 1/2. And so your coordinate is 3/4 and 1/2, right? That is the point where they would cross on your graph. Okay, so that is substitution. The next method is elimination. So to get elimination, you want to multiply each equation by a constant to get the LCM of a coefficient for one variable. So you either want to make them opposites or the same. It doesn't matter. It just means we're going to either add or subtract. So you add the equations together so that you can eliminate a variable. And then you're going to solve for the remaining variable and plug that back in like we did above. So for example, I look here and I can choose x or y. It doesn't matter which one you want to do. In this particular case, I have to multiply both equations. So I'm going to go ahead and do y because they're already opposite signs. So if I add them down, if they're opposites, they'll go to 0. So I'm going to multiply this top equation by 4 and the bottom equation by 3 because the least common multiple between 4 and 3 is 12. So I need to multiply by whatever will make them 12. This needs to distribute to everything, or it's no longer a proportional equation. So 20x plus 12y equals 36, every single term. And then down here I have 6x minus 12y is equal to 42. And so I add those equations down. 20 plus 6 is 26x. These will add to 0, which is what I wanted. And then these add to 78. So I'm just going to divide here by 26. And x equals 3. So once I know that x equals 3, I can plug it into any 4 of my equations to solve for y. And so I have 2 times 3 minus 4y equals 14. So 6 minus 4y equals 14. Negative 4y equals 8 if I subtract that 6 over. So y equals negative 2. And so that coordinate in coordinate notation is negative 2, where these would cross. All right, so we will go ahead and have you try these on your own and go over them in class together. All right. Word problems, don't overcomplicate them. It's usually one equation per sentence, and you're looking for the totals or the relationships between the variables that they give you in order to write those equations. So Weinborn has 35 coins. There's one of your total dimes and nickels. So dimes plus nickels will equal 35. All right. If the value of his coins, all right, so now we're talking about total value, is 330, then how many of each does he have? So a dime's value is 10 cents. So 10 cents for each dime. A nickel's value is 5 cents. So 5 cents for each nickel. And that total amount is $3.30. You can solve these with substitution or elimination. This one's set up very well for either method. And so go ahead and try to solve that as well. The next one is a boat traveled 210 miles downstream and back. The trip downstream took 10 hours. The trip back took 70 hours. And so this has distance and time going on in here. What is the speed of the boat in still water, and what is the speed of the current? So downstream, you're with the current, and upstream, you're against And so when your boat in still water, the speed of the boat is its own, but when you're going with the current, that's going to be helping you. And remember, rate times time is equal to distance, or distance divided by time equals rate. You could set this up either way. So this is the speed that it's going. The distance that it went when it was with the current was 210 miles, but it took it 10 hours to do so. And so distance divided by time. When you're against the current, it's pushing against you. And so you have the speed of the boat minus the speed of the current. It went the same distance, right? It went down and back. So it still went 210 miles, but it took 70 hours to do it this time. All right, so you could go ahead and reduce those so that you have B plus C. Let me keep that the same color here. You have B plus C is equal to 21. And then you have B minus C is equal to 3. And this one is actually perfectly set up for elimination. You don't even need to multiply anything. You can just add those down and solve for B. Plug that back in and solve for C. Okay, so that gets us into multivariable linear equations, which would be like a 3 by 3. So you have 3 equations with 3 variables in this particular case. Okay, so you're mostly going to use elimination with a small combination of substitution since we need to plug those values back in. Now, sometimes though, if you have a system like this, you can use double substitution. But most of the time, we're going to rely solely on elimination to get down to the value that we need. Okay. And so if you're using back-to-back substitution here, that's because we have an equation that we can solve right away. Z is equal to 3. And so I'm going to take that 3 and I'm just going to plug it into this next equation up. Negative y plus 3 times 3 equals 9. Negative y equals, or excuse me, plus 9 equals 9. So y equals 0. Subtract that over, divide by negative 1. So then I can replace both of those in the top equation where I have x plus 2 times 0 plus 3 equals 7. And so x plus 3 equals 7 and x equals 4. We can still write this in coordinate notation that always goes in alphabetical order. So 4, 0, 3. Sorry, I don't know what's going on here. Most of the time, though, that's not going to be entirely possible. And so what you're going to do is you're going to pick 2 of your equations to start with. And so I'm going to pick just these first and second ones. So we'll call that equation 1 and 2, or A and B if you don't want to use numbers. So x minus y plus z equals 2. Negative x plus 2y plus z equals negative 3. And then you're going to pick one variable to solve for. So pick 2 equations and then pick one variable to eliminate. This one is already set up to eliminate x, so I'm going to use x in this example by just adding these down. The x's will go away. That goes to y plus 2z equals negative 1. And we're just going to kind of sit on this equation for a second. Then you're going to pick 2 more. So I'm going to use 2 and 3. Negative x plus 2y plus z equals negative 3. The only reason I did this is because we have to eliminate the same variable, and these are already opposites. And so, eliminate same variable. So I'm going to multiply this top equation by 3. And that changes it to negative 3x plus 6y plus 3z equals negative 9. The bottom one is going to stay the same. Remember, sometimes you don't have to multiply both equations. Or if it makes you feel better, you could multiply it by 1. And then we can add down here. So the x's cancel. We get 7y plus z equals -7. We're going to take these two answers and match them together and create a new system. And so now we have 7y plus z equals -7. Right, and y plus 2z equals -7. Okay. After multiplying this top one by 2 to get the z's to be the same, because they're the same this time, I'm going to subtract down my equation. So I get 13y watch your signs here, and so y equals -1. You're going to domino that through, so you can plug it into one of these to find z, and then plug z and y into one of these top ones to find x. All right, the rest we're going to go through in class together.